everyone today. Hold on, let me just, okay. Our second presenter, Mr. Charles, is the sales manager from the NOVATIQ Scientific, Sdn Bhd. He graduated from UPM with a bachelor in biotechnology. Wow, same with me. Okay, he has strong passion in analytical line, especially in imaging and spectroscopy product, with over 9 years experience since 2012. Previously, he represent a well-known and high-end instrument manufacturers such as the Tascan, Linda, Sanying, Euromax, Oxford, and etc. He started his own imaging business in 2018 by establishing this company. And NOVATIQ Scientific is one-stop imaging solution center for lab furniture supplier in Malaysia as well. So today he will share about the lab instrument provided in Malaysia, especially the one that focus in technologies such as spectrometry, material characterization, X-ray imaging, microscopy technique, and you can just basically ask him anything about microscopy. So without further waiting, let us welcome our next presenter. Could you please give him a big applause, Mr. Charles? If you're ready, then you can just share your slides.
Yes, I'm ready. Yep.
Okay.
Okay.
Let me just stop sharing. Okay.
Okay. Share. Okay, I'm sharing the screen now. So I'm not sure, Doctor, you're able to see it?
You can see? Yes, we can see it.
Okay.
The first slide, advancements of SEM EDX. Is that correct?
That's right, that's right. So are you just seeing the slide only? Or you're seeing the notes also?
Yes.
Just looking at the slide only, right?
just the slide, not your speaker's notes. Okay?
Okay, sure. Yeah. Hello, everyone. Welcome to the webinar series. So-called Team SEM Imaging. So I'm Charles here, the speaker of this session. And thank you for taking the time out and being here today. So we just heard Dr. Juan, giving a talk on the different techniques in material characterizations. So especially the part for SEM and TEM. So that's very nice. Then I'm not sure, but do you know how advanced SEM can be? So that's why that's the topic of the day of this session. I'm going to talk more about the advancement of SEM EDX in material sciences, this field. Okay. Then before that, right, I would like to just briefly introduce my company, NOVATIQ Scientific. So we are a company specializing in imaging solutions. And you can see these are the product that we carry. The bread and butter of the company is SEM EDX, the ultra high resolution FE-SAM, the FIB SAMs. Of course, we have Raman SAM. Then we have those sputter coater. Those are the sample preparation tools to the SEM, including the ion miller. Then we do supply AFM also as well. And in case you're wondering, we have X-ray imaging, so the high resolution micro CT and come to the 4D X-ray imaging nowadays. So today we'll be looking into, so the next slide, right? We'll be looking into some of the histories, and also I'll be talking about the different types of SEM. So looking at this page, this is page number 3. So you're seeing page number 3, right? So looking at this page, you'll be seeing two pictures. These are the pictures of TEM, the very first commercialized TEM back in 1951 by Tesla. So you can see these are now antique no longer in use, but those are the days they commercialized the TEM back in Brno. So the origin of the microscopy is from Brno. Brno is from the country Czech Republic. Then this Tesla group, right, they last for a few decades and come to a point they dissolve. And then they form few companies, 3 companies to be exact, and one of them is Tascan. That's why from there onwards, Tascan started to venture into the scanning electron microscopy, this field. Yeah, so of course, there's a major breakthrough here in 2013. Yeah, let me show. Okay, put a note here. So 2013, Tascan merged with Osei Physics, the producer for FIB. So from there onwards, they started their FIB business. And to date, they have produced more than 3,000 systems of their system and being installed globally. So the stronghold of Tascan is FIB SEM. Yeah. Anyway, Tascan is just a brand of it's the producer, the manufacturer for the SEM. So we NOVATIQ here are representing their products. Then let's go into the real discussion of the day. So why do we need SAM for? And of course, is to visualize, sample, and characterize them, right? So when it comes to material characterization, right, there are actually a few capabilities that one researcher are interested in or looking for. Of course, the first one, they want to investigate samples with enough contrast and search for the level of details on the surface, right? So this level of details is defined by the resolution power. This is what the researchers always looking into that. Of course, for samples, it could be down to nano level nowadays. So it could be complex in form, it could be very complex in shape and also in size. So a SAM system, right? You must have a very fast and precise navigation equipped with this function. Then, of course, another capabilities that researchers always valued here is the capability of imaging samples of different kinds, especially the charging nowadays. Nanomaterials, they tend to charge. The sensitive samples under SEM, under the electron beam, and outgassing sample. Yeah. So, of course, SAMs must be able to handle this kind of samples. So, of course, there's always a need for material characterization. So not just visualization, but into the material characterization by microanalytical tool. So one example here will be the EDS, the energy dispersive tool. Of course, there are other detectors like EBSD, WDS, and so on. Still, do you think this will highlight how advanced the SAM can be? So not really up to here. So in this page, I'll be introducing you how advanced a SAM can be. What's what we discussed just now, right? Usually that can be achieved or accomplished by normal SEM. That's why here we have the high vacuum SAM. Bear in mind that SAM is always in high vacuum mode. So their construction of the column and chamber by default is under high vacuum. So this is the most commonly available SAM in the market, used to resolve to see the level of details. Yeah, and resolution type of SAM is fall under this category. Then of course, another level of SAM, we have a different vacuum level. We call it low vacuum SAM. It's meant for handling charging materials. But then low vacuum, right? What is sacrificed under low vacuum? It is the resolution being sacrificed. So what if I tell you that the advancement of SAM, right, go up to this level? You can image charging sample under high vacuum. This is some breakthrough, right? I let you think a bit. So this is something that you may not encounter before. So high vacuum, we do not lose resolution. We have the resolution there. At the same time, we can image charging materials. Of course, come to another category, right? We have FIB SAM, the so-called dual beam SEM. One of the column is electron microscope, and one of the column is the FIB column. This is another characterization level. So with much higher cost, able to resolve most of the material studies. That is the ultimate aim. So if you want to go further, we have Raman SAM, whereby we have Raman integrated into SAM, and utmost we have a Christmas tree. The so-called Christmas tree is everything in SEM. And in Tascan, they have all kind of products that I have just listed just now. So the first one highlighted in green, this is the normal SEM, be it a tungsten type or be it a FESAM type. Then we have the SEM able to see charging material under high vacuum. So this is by Tascan Clara. Then we have FIB SEM, the dual beam. So the dual beam, right? is highlighted here in the center image. Of course, we have Raman Sam, and this is the Christmas tree. Yeah. So worries not, we'll go through one by one. So this is the, of course, the first one we have to see the SE and BSE. I will highlight you these kind of examples here. So they are used to visualize, of course, for those charging sample, bear in mind you need to prepare beforehand. You need to coat it under sputter coater beforehand in order to visualize under high vacuum SAM. So by default, the vacuum level in SCM is highly vacuum. So first example here is ceramics. So you can see ceramics here, we can determine the level of cracks, the level of thickness layer here, and also some cracks over here. So this is pretty much the basic of SAM. And SAM, of course, give you some imaging on SE, so-called the topographical image, and the backscatter image by BSE detector, so-called the material contrast kind of image. And move on to metal samples. So this is what I want to highlight here, how SE and BSE image, right? They are complementary to each other. In this example here, corroded metal surface. So by the term, there's a corrosion there. So by the view under SE, you just see this kind of surface topography, right? But if you image or visualize it under BSE, you will get different kind of signal, especially this kind of material contrast kind of signals. So here you're able to determine whether the surface, how severe the corrosion happened on the surface, because under the material contrast, this kind of carbon, oxygen kind of elements, right, appear to be darker compared to heavier element. So in this case, BSE is pretty useful here in determining the corrosion of metal surface. Further, we have fibrous analysis, whereby we can determine the size, the diameter of it. So this is, and then further on, we have a high resolution imaging on titanium oxide particles, nanoparticles. You can see that down to this kind of marker level, we can measure the size of it. So this is achieved by high resolution SEM. Still, this is pretty common in SEM or FESM. So now I'm going to talk further into low vacuum SCM. So by default, SCM is under high vacuum. So in case you want to image any kind of materials, so example here, ceramics, they are charging in nature, we have to sputter coat it beforehand. So you will see clearly under the high vacuum SAM. What if you don't have sputter coater? Can you still image this kind of materials? Yes, you can. And just to let you know, if you do not coat the sample, this is its appearance. It appears to be charging. So these are the areas that is charging. So we under high vacuum. So we have to activate the low vacuum mode to resolve better. So a better image quality here, right? When it is under low vacuum mode. So this is how the low vacuum SCM come into play. And further, so just now we see this kind of image, right? Yes, you may resolve under low vacuum, but it is fully by backscattered electron. So backscattered, you do not get much of the surface topography information. So topography, if you're emphasizing here, so we have to use another kind of detector already. So actually, we have SC detector, which we call it gaseous secondary electron detector, to see surface topography under low vacuum. So you can compare just now an image taken under BSE detector, and this is the image taken also under low vacuum, but it's by SE detector. Now you see the difference, right? So the level of details is different. You can see this kind of structure is being resolved under the low vacuum by the SE detector. So this is what we want eventually. Then further, more example here, how we're going to review the finest topographic details. Yeah, from the beam sensitive sample, the charging sample under low vacuum, without coating. Yeah. So this is all achieved by the so-called the gaseous secondary electron detector. And of course, when we come to the this kind of level of imaging, right? Can we use low vacuum? Can we use low kV? Yes, we can use low kV to image the. Of course, low kV will give you more on the surface topography. That is why we use low kV instead of higher kV. You see, higher kV here, it tends to appear this kind of transparent kind of structure. But then if we resolve under low kV, 2 kV example, we see the tiny details of the topographical structure. So in low vacuum mode, you can use low kV, no issue. So what about this imaging charging sample under high vacuum? So have you ever thought of this? And now TestScan, we're able to do that already. So by imaging this kind of charging sample under high vacuum. It's not low vacuum anymore. High vacuum, we retain the resolution. The resolution is still there. We do not compromise it. This is what conventional SCM cannot achieve. So if you compare this charging image, charging here, and this is the refined structure image, which we're able to see this kind of details, level of details here. And bear in mind, this is butterfly wing is life science sample, image at 1 kV, is under high vacuum, we do not code it. So in TestScan SCM, we're able to resolve this kind of image already. Same as this is a moth wing, again, life science samples. This is a charging sample, the same image, the same location we taken here, right? One, we image under the chamber detector. Another one, we image under another kind of detectors. But I want to show you that we're able to resolve charging sample under high vacuum. So as this image, this is the graphene sample, the nanomaterials. So this image is taken simultaneously by 2 different detectors, and it seems that this chamber detector gives you a level of details refined. Yeah, so this is what we want. We are aiming for this kind of imaging under high vacuum. We do not compromise the resolution, yet we are able to see, resolve the charging light sample. And come to this pollen grain, yes, just to show you that how fine the details can be resolved under this kind of condition. Yeah, look at the surface topography information. Then come to the FIB. I'm not sure, have any of you heard of FIB SCM before? So can you, this is a dual beam system. So here, a dual beam, I call it dual beam because this is the electron column system, the SCM, and this is the focused ion beam system. Can you imagine that you have a tiny sample in nanoscale, you locate in the chamber, and you wish you can manipulate the sample, you want to trim down further the sample, you want to mill your sample, and you want to remove layer by layer the surface of the sample. How can we achieve that? So you imagine this, right? We can achieve, can be done by the FIB column. So with this FIB, we're able to mill, create some patternings, because the FIB will remove the material through the sputtering at very specific location, direct to the beam. This is the function of FIB. So it is a very powerful tool for site-specific 3D imaging of submicron features in the sample. Therefore, this is the keyword here. So in this FIB tomography technique, right, the sample, you imagine the sample is milled, is layer peel off by layer peel off, and then the is sequentially milled using the ion beam, right, to the specimen, right, while imaging. Then the newly exposed surface, will be captured by the SEM and then reconstructed into 3D form. So this is, we call it 3D structural analysis by the FIB SAM. So, okay, right? Up to this level. And actually, there are 2 types of FIB. There's gallium FIB There's very common or conventional FIP, and there is plasma FIP, the most advanced FIB system nowadays, whereby the opening size here is very wide. Look at this marker here. This is about 1 mm opening size. Compared to this, it's just 20 micron opening size. So this is the different kind of FIB available in the market. So of course, they do the same task. They mill the sample, they manipulate the sample, trim the sample. Yeah. Then let's take a look at this application, the battery application. So lithium-ion battery, the material kind of sample. So of course, you know that battery is the leading energy storage for. They are very useful in electronic portable device or even in hybrid vehicles. So purely the analysis of SCM, right? You know, is no longer enough. That is where the FIB SAM come into play. So simultaneous characterization of the structural chemical, the chemical compositions, and elemental distribution in the lithium-ion battery, right, is always the aim. So therefore, you can see that I just want to show you the gallium FIP performed here, right? Due to the small opening, it can only resolve limited structure compared to the plasma FIP here with a very large opening here. So in this case, we use FIB to study this, whereby the large volume analysis is beneficial for 3D, 3D study of degradation of lithium-ion battery during the charge cycling. So this is the case here. And then a video is being shown here. I want to show you how FIB SAM tomography, or we call it 3D reconstruction of the FIB SAM, right, being carried out. So imagine this is destructive technique. Then FIB is milling peel off layer by layer. At the same time, SCM is taking the images. So when come to a point, the software able to reconstruct them into this kind of 3D form. So with this kind of capabilities, the volume analysis, or we call it FIB-SAM tomography, or we call it 3D analysis, is able to achieve using this FIB-SAM. So this is another kind of example here. When we are able to achieve this kind of evaluation, right, we can go further to enhance the characterization by EDS, the elemental analysis, and EBSD, the so-called the crystalline structure kind of analysis. So we use these two detectors concurrently with the FIB SAM. We generate a pool of data here. We can have this 3D tomography reconstruction. We can have EDS and elemental analysis data here. You see, this is the SN element, the lead element, and then we can have crystalline structure, crystalline detail information from the EBSD. So all information in just one tool. So you can imagine this, right? This is how the level of characterization we can use in FIB SAM. So we have the SCM, we have the FIB, we have the EDX, we have the EBSD. So this is very useful for the researcher for the material characterization. So further to that, we can do statistical model also. So after this kind of pool data collection, right? So we can further analyze the phase identification, its distribution, its grain size, etc. So they are tabulated here, showing different kind of information, but these are the collected statistical data. So can it go further? So after we talk about SAM, FIB, 3D EDX, and 3D EBSD, bear in mind it's 3D because we create a volume. Yeah, we reconstructed them in a volume. That's why I call it 3D. So can it go further? The answer is yes, we can go further analyzing with TOF SIM, the time of flight secondary ion mass spectrometer. So take one example here, the lithium ion battery. After we have the 3D information being reconstructed here, right? So we can actually analyze this under TOF SIM. So as you know, the lithium ion battery EDX is a common elemental mapping technique. readily accessed in SCM. Any kind of SCM, they have the EDX. But then do you know that EDX is limited to certain elements? Like elements like lithium, they are not able to detect it under EDX. So we have to use TOFSIM. The mass spectrometer will cluster them and then show the lithium information. So this is the TOFSIM map. So we're able to map it, able to thus determine the distribution of lithium in this case. So my answer here is we can further analyze by FIB-SAM plus a TOFSIM detector. So I'm not sure whether you all know TOFSIM or not, but in case you're wondering what is TOFSIM, right? It is sensitive. It is sensitive to ion. They use primary ions to generate secondary ions. The ions is captured by the TOFSIM detectors. Yeah. Then come to another level. So we discuss about FIB-SAM technique, specifically in a plasma FIB. But then there's another advanced technique we can couple with Raman, right? I don't think you heard of this Raman, but do you know that universities in China, right? They purposely acquired this kind of system, the Raman SAM, to boost their ranking. Yeah, this is how Raman is being popular in China and other countries. So in TestScan, they call it RISE, the so-called the Raman integrated SEM. So they call it RISE. So in case you wonder what is Raman, Raman is for the, the spectroscopy technique is for the chemical compound analysis. So if you, this is brief elaboration of what is Raman. So coupled with Raman here, right? So it will bring a very powerful analytical tool, giving the chemical and structure elucidation, the structure characterization. This will be benefit by using TestScan, by using the SCM plus Raman. So performing this kind of simultaneous analysis, right? This is the most complete analysis applicable to material characterization. It can be used in nanotechnology, optoelectronic materials, pharmaceutical, geology, minerals, forensic science, and so on. So these are the field they are applicable. So this is how the construction of the Raman inside the SCM chamber. So the Raman, right, they have the Raman system. Let's say the sample, the Raman is analyzing this spot, right? The whole stage, it will be moved to the SCM part and analyzing the same spot as well. So we call it correlative imaging. So the same spot we use to analyze Raman, we can use for FIB SCM characterization, coupled with EDS, EBSD, and we get all sort of data already, even coupled with TOFSIMs. So you can imagine this, right? This is how the Raman look like. So let's look at one example here, the graphene layers. Very popular topic here, graphene layers, especially the G-band, G-band here. This is direct proportional to the number of graphene layers, the intensity of the G-band, yeah. So the higher it is, the more layer it has. So here, right, we're able to first analyze under the SEM, then go for the Raman. In this case, it's Raman imaging. The Raman map the whole SEM image here, and then give you this kind of colors, and then we can pinpoint this. Oh, green is belong to this kind of multi-layer graphene. Blue is belong to this kind of bilayer graphene. Red is belong to this kind of mono-layer graphene. Yeah. So let's look at another mineral example here. Of course, mineral, they are sensitive to, they have the Raman information. Yeah, the Raman shift. So from there onwards, Raman is a very suitable technique. But in this case, I'm coupling this with the SCM imaging. So here, I first get the SCM image, but I do not know what are the compounds or different materials present in the SCM. I do not see that. I will not be able to know unless I go for Raman. I do a Raman mapping. So Raman is specifically mapped in this region in this case. And here I be able to pinpoint, oh, this is the feldspar, and this is something else, and this green color is something else, and so on. So this is how Raman and SCM beneficial to the material study. So last thing, this is the Christmas tree. And when come to this Christmas tree, you just imagine you have everything under one SCM. So SCM is just a platform for imaging. And it depends on how you're going to equip the system with. You can equip the system with, of course, SE and BSE, very common. It's a must to have for topography and material contrast information. Then EDX is the secondly common detector that always can be found in SCM for elemental analysis. Of course, nowadays, researchers tend to couple with EBSD for the crystalline structure, the orientation, the phase study, this kind of studies. Then the rest is not so common, but it's very advanced if you have it in your facility. So I described about Raman, I described about TOF SIMS, I described about the 3D EDX and EBSD. Of course, this can only be achieved using FIB. So you can see this is the FIB column here. Then you can even equip with other detectors. Actually, there are many detectors in the outside. So yeah, so Christmas tree is like having everything in. So here you can see, look at this image here. Look how complex this SCM is. So bear in mind the sample chamber has to be very big in order to fit in all kind of detectors. So this is how I'm going to end my presentation. I know it's a bit fast, but in case you have any question, right, feel free to ask me. Yeah.
Okay. Thank you very much, Mr. Charles, for the, I think, very interesting talk. I think we can see really nice images. So I would like to welcome, I would like to welcome Dr. Juan and also Charles together to answer, I think, questions, burning questions.